All right. Good afternoon, everyone. And thank you for making the time and coming to the LinkedIn session. And first of all, congratulations for making it. This is the last day, last session almost, and this is the last Hadoop Summit of the year. So congratulations to all of you. Hope everyone has achieved a lot of clarity around the different ways in which you could be doing BI better, or maybe doing machine learning just that little bit better, or running your queries 10 times faster on Hadoop. But who's feeling like this? Anyone? All right, cool, great. So, well, we at LinkedIn have been feeling this way for quite a while now, since 2009 when we started using Hadoop and tried to make it work for building data products. And LinkedIn has like tons of data products. People you may know, jobs you may be interested in, ads you may be interested in, maybe news you may be interested in. And every single time one of these data products gets built, the engineers have to go and figure out, okay, how am I going to build this? What am I going to connect to? How am I going to process this data? How am I going to put it back to the site? And over the years, we've kind of learned a few things, made lots of mistakes, and we're still learning. But today we are here to maybe show some experiences from building these systems and help you all get a little bit clarity in your lives. Because the way we survived so far is by thinking about life in this way. You've got three phases: the ingest phase, the process phase, and the serve. And then right in the heart of it all is metadata, right? And let's look at PYMK. So how does PYMK work? We ingest all our data from the online databases where you've got your connections data, your address book, maybe tons of different skills, things like that. And then you're doing a bunch of activities on the site. You're looking at people's profiles, you're maybe responding to emails and things like that. And all of these get pulled into Hadoop, and then we do a bunch of fancy algorithms on top of it, and then create suggestions for what people you should be connecting to. And those get pushed out to Voldemort and then served back to the site. So ingest, process, serve. That's how we built it. But let's focus a little bit more on each of these pieces and talk about how we've tried to simplify our lives in each of these areas and where life actually isn't very simple. So let's start with ingest first. And so this is circa 2010. We had quite a big problem. We were happily connecting different systems to different other systems and creating quite a nice mess. And then we said, wait, we've got to stop doing that. We've got tons of data quality problems. People are complaining. They fix one pipeline, and the other pipeline is now giving problems and things like that. So we said, well, we've seen the light. There is a log, and the log is at the center of the universe. And we're going to make everything look like a log. So we tried getting our database changes streaming out using change capture from the databases through the system called Databus. And then we had Kafka to basically ingest like tons of user activity logs, anything you name it, all goes through Kafka. And then everything else downstream from that, Hadoop, the search system, the graph system, everything was pulling from there. And we thought, OK, this is a good step forward. But then people kept coming back to us and saying, data quality, data's not arriving on time, and things like that. And we started looking, wait, what happened here? And we turned out we actually still had a problem. We had focused so much on the streaming data, and we tried to get all the streaming data unified, and that was a good step. But we also had a lot of not so streaming data, files that people were sending to us, or connections up to Salesforce where we would pull down data at the end of the day. We were acquiring companies. Some of these companies do business in S3, and that's where we have to get our data from. And even databases like Espresso and Oracle, they were doing bulk data dumps every night or every other night, and that data also needed to come in. And so for Hadoop, there was quite a bit of ingest complexity still remaining to be solved. We had individual ETL pipelines for each of these different sources, and the same problems every time, right? Data is not there on time, or data is there, but it doesn't quite look right. Or I got some data from here, and I've got some data from the other system. Now I need to mash it up, but they're not really consistent. So what we basically realized was that ingestion was giving us indigestion. And so we had to get way better at gobbling all of our data into Hadoop. And so we came up with this crazy name called Goblin. And we basically said, let's centralize the ingestion framework step one was centralizing the transport pipeline, and step two really is having a central ingestion framework, which connects up to the central pipeline as well as all of your other data sources so that you have a single way of looking at the world and bringing data in. And at the same time, we started doing things like standardizing the way we do compaction of these data sets, some amount of lifecycle management like retention, adherence to European compliance rules and things like that. And so that's kind of been our journey. And when we started on this, we looked around and said, hey, what are the requirements for this system? What are the things that we really want to make sure we're solving for? And of course, source diversity was number one, right? That was the primary challenge we were dealing with. But we were also seeing this batch and streaming unification happening, that some data for the same data set is coming in from a batch system, and some different data for the same data set is coming in from a streaming system. We were having snapshots coming in from filers and incremental data streaming in from Kafka or Databus. And so we wanted to say, we want one system that can look at both of these data sets as part of the same data set and holistically merge them and things like that. And most importantly, data quality. This was something that everyone kept talking about. It's kind of this hard problem. It's vague. You can touch it from this side, and it looks like schemas, but then you touch it from the other side, and it's business rules. And it's really a complicated problem. But data quality kept coming up again and again, and we said, we have to make sure that data quality is a central first-class citizen in whatever we build. And we looked around at a bunch of open source frameworks. Some we had ourselves, like Camus and Lumos, and we realized that not one of them really addressed all of these, and we set out to kind of solve all of these using the same system. So fast forward to today, we've got something called Goblin. It's open source. It's got a reasonable architecture. We've tried to modularize everything. We've tried to create concepts that make sense. Extractors, quality checkers, writers, these are first-class concepts. And everything is as pluggable as we could make it. So if you have a custom use case, you can always swap out one thing for another. And we tried to keep the metadata and the monitoring piece constant, because those were the two things that we felt had to be the same for every single thing. And we tried to make the deployment capabilities a little more flexible, because we said there are some cases where you need a single node kind of deployment. In some cases, you need a distributed, maybe Hadoop-based deployment. In some cases, you need a standalone or maybe Yarn-based deployment. And so we wanted to keep that deployment layer flexible. So this is kind of what the Goblin pipeline looks like in general. There's a concept of a source. The source essentially is partitioned, so it generates work units. And all of those work units get passed through a pretty simple pipeline of extraction, conversion. This is where you could be doing simple transformations. We've tried really hard to stay away from the slippery slope of putting lots of transformation capability inside the pipeline itself, because there are data processing frameworks, and those are great for doing transformations. We didn't want to reinvent another DAG execution engine. So we said we'll have a simple ELT kind of framework, because that makes the most sense. And the conversions primarily are for basic schema changes or things like security concerns where a certain field needs to get elided completely from the record or anonymized or things like that. And then quality checkers that run. And then finally, there's a data publish step where the data gets finally released for downstream consumption. So for source diversity, we basically thought about it in a protocol-based way, saying there are a bunch of standard protocols, we'll implement them, then we'll build source capabilities on top of it. Old hat, nothing new here. We've got a bunch of sources that are packaged as part of the catalog. Salesforce, Kafka, S3, those are I would say, the most used ones. And then something we are working on right now is really solving for real time. So remember how I said we wanted to connect up to real-time sources as well as batch sources. And when you're trying to ingest data in batch, and this is something we've done for a while. Even our Kafka pipelines run on Camus, which is a mapper-based system. Every 10 minutes or every 15 minutes, a bunch of mappers come up, they ingest some data, and then they go back to sleep or shut down. And then another 10 minutes later, another batch comes up. And we noticed that there was a lot of inefficiency in how this whole job setup was happening. You wait for getting containers or tasks, and then you get your slots, you get on them, then you ingest data for a little bit of time, and then you give it all away, right? And even tuning these jobs gets hard because during the day, you've got a lot of traffic, and at night, you've got very little traffic. Then you have to have your MapReduce config kind of optimized for that to figure out how many mappers to spawn. And so we ended up saying, let's actually solve for real time, in real time. So what we did was now with Hadoop 2, since we have Yarn, create the ability to have executors get spun up and have those executors run for a while. And they're basically continuously ingesting from the stream. And they're actually scaling in and out. We use Helix for cluster management. So that way we can adapt to the stream capabilities itself. And then the final thing, of course, is data quality. So data quality, I would say, is a thing we've done quite amount of work on, but there's still like miles to go before we sleep. We've got quality checkers that are running per record or per task or per entire job, and they're doing things like checking for schema compatibility, doing audit checks to make sure that the number of records that a certain window of data has is actually found, looking at sensitive fields, PII, and things like that. And we have a lot of work left to do, but we've got some basic policy configurations in here where you can say that, OK, if a certain quality checker fires, I want the data to be, those offending records to be quarantined, or maybe I want the entire pipeline to fail, or I want to just log a warning and monitor it and move on. So we've got a couple of flexibilities that have just come out of trying to run these pipelines and seeing what happens. So current activity, it's open source on GitHub. I think we've kind of done a silent, dark open source in a way, probably 3-4 months ago. And it's been in production at LinkedIn for about a year already, and we're doing tens of terabytes per day, hundreds of data sets. And most importantly, around 20 very different sources that we're pulling data from. And most of the current quarter's activities are around productionizing our Kafka pipeline and getting the Yarn-based integration to work. So that's kind of the roundup for how we try to solve ingest. So let's get into process, the processing phase, which is you've got your data into your lake or river or whatever, pond, whatever you would like to call it, and then you want to process it. And guess what? You've got lots of different tools to process the data. And what we've realized is, each of these have their own sweet spots. If you've got your data mostly in memory and you're doing iterative machine learning stuff, use Spark. If you've got batch ETL jobs, you might use Pig or Hive. If your programmers like to work in an IDE and they like writing type-safe workflows, then Scalding is the way to go. And then if nothing works out, then roll up your sleeves and you write some MapReduce, right? So who's writing MapReduce anymore? Anymore? No more? Yes, good. We're not writing MapReduce either. We've got a bunch of old stuff that was running MapReduce, but most of our analysts, most of our ETL engineers, they end up writing Pig, Hive, Scalding, Spark, some of it nowadays. But there are some times where these actually don't quite do the job. So we found cases where intermediate data sets are like trillions and trillions of records, where most of the focus here has been let's shoot for kind of the interactive query latency, bring that down. SQL on Hadoop, that's where the focus is. And then Spark is trying to, again, leverage the aggregate memory of the cluster. And what we found is there are certain Hadoop workflows which run for hours. And those are because they're running batch ETL, they're processing large amounts of data and generating a lot of intermediate data sets that are pretty large. And for those, people have kind of come to be expecting that, yeah, it's going to take a few hours, right? And that's fine. It's a nightly job. But what we found is, there's some amounts of improvement that can be done where you can actually bring those jobs down by, sometimes orders of magnitude. So we built this thing called Qbert, and it came out of, our problems with trying to get Pig and Hive to work well for an extremely large analysis use case when we were doing A/B testing analysis. So everyone who's coming to the site is getting put into God knows how many experiments. And then for each of the experiments you're part of, you're either in the control group or in the test group. And then based on that, we try to calculate which of our metrics got impacted by what you saw and what you did. And it's a crazy join. And so statistical calculations, we saw a lot of improvement there. But then, interestingly, we started looking at triangle closing, which is a common thing done in PYMK, which is a second-degree kind of join. And there we found a lot of improvements as well. We found that we were able to bring the triangle closing cost down quite a bit. So graph computation seems promising as well. And then we also had a reporting pipeline, which was doing a lot of cubing before loading the data up into the data store for serving. And we saw a lot of speed up there as well. So it's pretty interesting. Qbert has actually solved a lot of niche problems for us, and we continue to use it in interesting ways. And most of it is because it's got paid a lot of attention to organizing the data before it actually starts going against it. And so there's a lot of block organization, memory disk layout stuff in there. Really, if you think your Hive jobs or Pig jobs are running slow, I would advise you to check it out. It's on GitHub. So let's get back to meta, because meta is at the heart of it all, metadata. And like I talked about a few minutes ago, we tried to centralize our ingestion pipeline, so that's good, because the fewer different things, the better, right? On the transformation side, we are not so lucky, because you've got different transformation engines, Pig, Hive. We've even got some Teradata, and we've got Informatica. And so the transformation landscape looks a little diverse. But then we also have tons of different schedulers. So we've got Azkaban, Oozie, AppWorks. We've got Easy Data, something we built in-house. And then we've got a ton of sources and sinks where data is coming from and data is going to. And all of this just explodes the number of combinations of sources and sinks and the paths through which and the frameworks through which data flows. And what that leads to really is knowledge silos. So you have teams that, for example, love Azkaban and Hive, and they love Hadoop. And they will create pipelines. Most of their pipelines deal with these systems. And then you have other teams that maybe love Teradata and AppWorks and Informatica. And that's like yet another system. But then these groups really struggle to share data with each other or share common understanding of derived data sets or sharing understanding of where data is coming from. And that leads then to the rise of these data experts in each team. So they are people who know about all these data sets, and if they're on vacation, then it's a problem, right? But when they come back, then they help everyone out. And we had a team like that. It was called the Data Warehouse team. They're still around. It was a centralized team, and they are still entrusted with creating this cathedral of data sets that everyone else depends on. And very soon, what we had was questions like these, like, where is the billings data? How did it get here? What data is used to create this derived data set? Who owns that flow? Because I'm going to change something. I want to talk to that person. And then, oh, my job just failed because profile data is not available today morning. When will it show up? Does anyone know? And there was a huge line in front of these people, and they were just struggling to keep up with actually doing their real job. Instead, they were just sitting around answering questions and creating curated data sets for people. And we said, well, this is not scaling very well, so let's try to create a more democratized self-serve model for this. And so we had started with these questions, right? Where is my data, and how did it get here? And we said, OK, let's create a project out of this and call it Warehouse. Everyone get the joke? The Warehouse team built the Warehouse portal. So the Warehouse team is now pretty happy. They're actually all attending today. Because they don't have to sit at their cubes and answer questions all day. And what it's done for LinkedIn has been pretty interesting. It's actually empowered the analysts to share data and collaborate across a large group. And essentially, it's a big scavenge and scatter-gather kind of operation. We've collected what we call technical metadata from all of the different data catalogs, HCAT, the Pig stuff, Informatica, Teradata, and then even scrape code repositories, right? And then when these processes run and the workflows run, then we're getting operational metadata, the job execution history, data delivery, data access, and things like that. And we essentially use a logical metadata bus to get all of this data into a centralized repository where it's organized for access, and this is the raw metadata. And then the community comes in and puts their business glossaries on top of it. So someone might say, hey, this column is not that good, don't use it, or this column was only introduced in the last March, and so before that you should use something else. And so it's kind of taken a life of its own, and we're pretty happy with it. So a day in the life of an analyst. Let's say you joined like a week ago and you're trying to figure out, hey, how does LinkedIn calculate page view events, or how do we count the number of page view events? So you might actually go into the portal, you get presented with kind of this simple entry screen, and then you can type in page view event. And lo and behold, you get a bunch of data sets that are all page view events of different forms, and the top one actually is the one that you want. And you can actually click through to that. And then you get comments, when was the last time it was downloaded. People are put comments. You can look at the schema. And let's say you look at something called viewer URN, and you're like, when did viewer URN come in? Because the last time I wrote code against page view event, I actually didn't use that field. So then you can go into a schema history page where you can actually look at how the schema of this data set has changed over time and which columns got added when and things like that. And that really helps people understand the evolution of these data sets, because these data sets are really not static at all. And then, of course, for power users who have kind of gotten used to the tool for a while, they can go in and really search for particular sources, do advanced search capabilities and things like that. So that's how you kind of solve the where part of the problem. Like, hey, where is my data? How do I find the right data sets? And then you have to solve the how. Like, OK, how is this data set getting used? And so for that, we have lineage, right? So this is where everything comes together, the data set metadata, the process metadata, and the operational metadata. And so you can start with page view event, go downstream, and look at how derived data sets are getting created. If you're lucky and we've been able to scrape the code for these pig scripts or Hive queries, you can actually click through and look at the code so you understand how these data sets are getting processed, which is pretty amazing because we like to copy code because generally code that's already running in production is good, and it's the right way to process that data set. And so we've focused so far on kind of the batch ecosystem at LinkedIn, so Hadoop and Teradata. And we're really thinking hard about integrating the streaming ecosystem as well, so the Kafka and Samza processing. And also bringing in some more machine learning so that we can recommend data sets to you, that recommend metrics that are related to this metric that you're looking at. And because we've had a lot of success with it, it's been around for the last year, I think, and it's been truly transformative for the company. We're exploring open sourcing it because metadata seems to be like a recurring theme. People keep talking about it every conference I go to. So we'll see if open sourcing makes sense and how to kind of layer it so that it kind of works for everyone. So that's Meta. And then Kapil is going to talk about the serve ecosystem.
Thanks, Shankar. Is this on? OK, so now that we've talked about the ingest phase and the process phase, let's talk about the serve phase, right, which is presenting the results and the insights from your computation back to the users. So earlier, we talked about different data products like people you may know. And there is a lot of data products that follow that pattern of ingesting the data into Hadoop, doing some computation, computing the results, and putting it in a key value store like Voldemort, which can then be served back to the users. But increasingly, we're building a lot of real-time analytics applications where the user experience has to be on real-time data and an interactive experience. And this is one of my favorite applications, I'll admit, on LinkedIn, which is who viewed my profile. Right? Come on, who doesn't like to go and check out who else has been viewing their profile, right? So people who viewed my profile not only shows you how many profile views you've had in a certain period of time, say last week or 90 days, but it lets you analyze and slice and dice that metric by a variety of dimensions. Right? For example, you might want to know, what do your viewers do? Are they software developers? Are they recruiters? Are they salespeople? What industries do those views come from? Or which companies do those viewers work at? Which geography do they reside in? So similarly, you can analyze this metric by any number of dimensions and any combination of those dimensions. And we have a lot of new data products that fall into this category. So how do you build a data product like this? So the first attempt was, well, it's simple. Let's pre-compute everything, right? So let's figure out all the possible dimension combinations that the user can possibly ask, compute those upfront, and stick them in some key value store. For example, if we have that same data and 2 dimensions, device and geo, we compute all the possibilities. We have the views for Android, iOS, the US, India, combinations of Android and US, so on and so forth. And when the user requests it, we just look up that key value pair, return the value as the answer. That seems pretty easy, right? Well, turns out it's not quite so easy. when we add a new dimension, the amount of precomputation that has to happen in order to figure out all those possible answers just grows tremendously. And this is only when we added one more dimension to this small data set of 3 rows, right? The real life data sets that we have are literally hundreds of billions of rows and hundreds, if not thousands of dimensions at times. And that is a lot of very expensive precomputation to do. So there are, of course, a bunch of commercial and open source solutions that can satisfy this pattern of use case. But we had a lot of very specific challenges that we had to satisfy. First of all, a lot of these data products are site-facing, which means that the latency they have to satisfy is extremely low, of the order of milliseconds. Also, these applications require very fresh data. You want to be able to query data that was just created maybe like a few seconds ago. Right? Lag of hours even is not certainly acceptable. Given the scale of the data that we have, we also need a distributed system that can scale horizontally and has very high, very low tolerance for any faults. And we can guarantee very high availability. And of course, to fit the use cases, we needed a lot of these OLAP features. And at the time we started building these data products, we looked around, and there wasn't anything that really satisfied all these requirements well. So we started building a new distributed OLAP engine we called Pinot. And why did we call Pinot? Well, the answer simply was that the team that built this liked to drink Pinot. So there are a lot of features that we built into this system, but a few that we paid close attention to. First, we wanted to make sure that the ease of use is kept in mind. So we provided a SQL-like interface, which most people are familiar with. To provide efficient query processing and low latency, organization of the data is extremely important. And I'll talk a little bit about the columnar storage and indexing techniques that we use. And again, we have to be able to query real-time data. So supporting real-time data loads is extremely important. So first, let me talk a little bit about the language, which is, I would say, SQL-like. So at least as of now, in order to keep a predictable query performance, we have not implemented joins. We might change that in the future. But we support a wide variety of other language constructs. So typically, the pattern is denormalize the data upstream, either in Hadoop or in Kafka streams using a custom job or Samza job. And we ingest the data into Pinot. And then we can do a variety of operations like filtering on different columns, a variety of aggregation functions. You can group by a different number of columns, order by limits, and a bunch of other features that you would want. Now, in order to support efficient query processing, the storage that we use in Pinot is a true columnar format. So every column in the data set is stored as a separate chunk of segments, and each segment is then compressed using the best possible algorithm we have given the data type of that particular column. And we implement a lot of the standard compression algorithms, like you have run length encoding, you have global dictionary encoding, and so on and so forth. Now we implement for indexing, we implement things like inverted index, but we also have a couple of additional cool tricks, and one of which is like a sorted forward index. So imagine if you have a column like a model, and this is car models where you want to filter by columns. You could write a scan, and we could scan that entire column extremely fast. But you could do even better if you had the column in a sorted order, and we can keep a data structure that essentially maps every model value to a start doc ID, which is equivalent to a row ID, and the ending row ID. Right? So now when you get a query that says filter on a particular column, a model value for that column, instead of scanning the entire column, you can just consult the index, identify the row IDs that you need in your data set. And there are many other indexing, sophisticated indexing techniques that we implemented in Pinot. In terms of query processing, in terms of a real deployment of Pinot has a large number of machines which are centrally managed by Apache Helix, which is a generic cluster management framework we built at LinkedIn and then open sourced as an Apache project. And Helix powers not only Pinot, but a host of other distributed systems at LinkedIn and also at many other companies. So Helix assigns different roles to different machines in a Pinot cluster. For example, we have real-time nodes that ingest data directly from Kafka, and sometimes which are computed by Samza jobs, and then put it back into Kafka. Periodically, we ingest the data back into Hadoop, where we process it and recompress it in order to get better compression ratios, which we then load into what we refer to as the historical nodes. Now, when a user query comes along, the brokered machines consult the metadata, identify which partitions and which machines to send the queries to, issue a scatter-gather query, collect the results, and then they go back to the user. So that's sort of the high-level architecture for Pinot. Now, as we scaled and launched more and more use cases, we realized that Pinot is extremely fast at processing queries, right? And we're not only limited to memory. We do memory mapped files and can page data in and out. But for a lot of cases where the latency is extremely critical, when you need millisecond level latency, you really have no choice but to make sure that the data fits in RAM, and you don't want to pay the cost of disk paging, right? So we have a choice, right? Either we can pre-compute the answers and store them in a key-value store, but which is very expensive pre-computation, or we can choose to keep the data in RAM and then query it at runtime. But if your data set is large, that's also pretty expensive. So we were convinced there had to be a better way. And indeed, there was. So going back to the precomputation, the reason precomputation becomes really expensive is upfront, you don't really know which dimension combinations the user is going to ask questions on. So you really have no choice but to compute the entire universe of dimension combinations and storing those data sets. But what if there was a way to compute just the right set of dimension combinations and leave rest of the data as raw data? Then we could cut down on the precomputation, but then the question becomes, how do you know which ones to precompute and which ones not to if you don't know the workload in advance? And turns out the answer is, in fact, in the data itself. And we let the data guide the storage and the data organization. And let's take a simple example. So let's take a data set of the same profile views. And imagine we have two dimensions like before. We have the country dimension, and we have the device dimension. Now, if you are trying to answer a question like, how many views did I get in US? Chances are that's a lot of your data, assuming most of your traffic is coming from US, and that's going to be very expensive to scan at runtime. So it makes sense to pre-compute that result. But on the other hand, if you're trying to answer a question about, say, Zimbabwe, where chances are you're not going to get a lot of data from, you can leave that data as is in raw form without pre-computation, and when the query comes along, you can scan the data extremely fast. And we use that same principle in order to keep branching and splitting across dimensions, and we stop branching when the number of rows in that partition falls below a certain threshold, and we know that we can query that within a small amount of time. So with this data organization, it turns out that you can pretty much answer a query on any dimension combination within a fixed amount of time. You start traversing from the root, and you stop either when you found the answer or you hit a leaf node, and then you can just issue a scan on the leaf node. But given Pinot's fast columnar scans, you can answer that question very, very quickly. Another benefit of this data structure is also that we can incrementally maintain these counts as fresh data is coming into the system. So Pinot has been a massive success at LinkedIn. And it has allowed us to build data products that otherwise would have been either impossible to build or at least extremely difficult, right? And a lot of the initial motivation came from having to build site-facing products like Who Viewed My Profile. But increasingly, we are leveraging this technology also for a lot of internal reporting use cases. The one you see here is called Excellent, which is our A/B testing platform. And Pinot allows us to analyze the experiment results along a variety of dimensions. And another interesting use case where we increasingly find that Pinot can be applied to is what I would call monitoring use cases, right? And the screenshot that you see here is actually a screenshot of how we monitor the usage of the jobs on our Hadoop clusters. And there are a lot of tools out there for monitoring the cluster itself, but having this data in Pinot allows us to slice and dice that usage data by user ID, by organization ID, by workflow type, and so on and so forth. Now, especially around monitoring, we are increasingly finding that the world of operational monitoring and the world of traditional business intelligence are colliding, right? And there is an increasing need to monitor your business metrics as well. And this is something you'd typically end up doing, and this essentially shows a week-over-week comparison of one of our growth metrics. And you'd note that around April 3rd, there was a significant drop compared to the prior week. Now, when something like this happens, the analyst has no choice but to go back to the raw data set, start forming some hypotheses, issue queries, and keep repeating that process until you hit the answer. But since now in Pinot, we are able to materialize just the right set of dimension combinations and incrementally compute the metric for those dimensions, we can actually do this on the fly. And we can compute the week-over-week or month-over-month numbers and start displaying them in a pretty easy-to-consume heat map format. So in this example, where we had a metric drop around April 3rd, just eyeballing the heat map showed us that, hey, there's something going on in Portuguese and Spanish-speaking countries. So, okay, we have narrowed the problem down, and we can click on the Portuguese data and drill down into, oh, what's going on? Oh, seems like there is something going on in Brazil. So then, you can use your favorite search engine. In this case, it's like, okay, we checked, okay, what's happening in Brazil on April 3rd, and Google answers that, oh, it happens to be a big holiday in Brazil and many other Spanish and Portuguese-speaking countries. And that pretty much explained the drop. But there are a variety of other use cases where, without a system like this, it would have been either impossible or would be very painful for the analyst to come up with analysis like this. So in summary, we talked about the 3 phases of the big data pipeline. We talked about ingest, we talked about process and metadata, and we talked about serve. And in each of these, we've built tools. First, Goblin for ingest, which we've open sourced. Qbert for processing, which we've also open sourced. And every time we've talked about Pinot, everyone gets very excited, and they always want to know, the first question is, when are you going to open source Pinot? And I usually have to explain, saying, yes, we are working really hard on it. The team is working 24/7. We are open sourcing it very soon. And for the first time, I'm really excited to be able to give a different answer, right? And this is the first audience we're sharing this with. And Pinot is open source. So you can go to GitHub or LinkedIn page and check out Pinot. And if you have a real-time data analytics problem at scale, I'm sure you'll find it extremely useful. So thank you, everyone, for coming to the talk. My name is Kapil Surlakar, and my colleague is Shirshankar Das. I hope you found this talk useful. And feel free to check out our GitHub page and check out our open source projects, Goblin, Qbert, and Pinot, and a bunch of other open source projects as well. Thank you very much.
Good questions?
So we just have a minute and a half, so if somebody has a quick question, we can answer now. Otherwise, we'll hang out here later. So feel free to come and chat with us.
Do you mind using one of the mics?
I think I heard this. So the question was, where do we store the historic data? So it's on the same Pinot nodes. So the Pinot cluster basically just appears to be one giant cluster of very similar looking machines. And the cluster manager, which is Helix, is assigning different roles to different machines. So some of the nodes are designated as historical nodes, and they pull in data that is compacted from Hadoop, and that gets pushed into those historical nodes.
Yeah, I was just curious to know if you had considered any of the other solutions that already exist, like Druid or Vertica, et cetera, et cetera.
Yeah, so the question is, did we consider other solutions like Vertica, Druid, and so on? And yes, this space is definitely very active, and you will find tons of solutions that might fit your particular sweet spot. But as we said, the set of challenges that we had in terms of low latencies, enabled to having solid cluster management that we can have 4 nines of uptime and beyond in terms of SQL support. We couldn't, each of the solutions that exist out there will probably give you, maybe half of what we were looking for, but there wasn't anything that satisfied all of our use cases. So which is why we made the choice to build our own. And all these solutions have sort of evolved since then, but I think Pinot still provides like some of these data structures and indexing implementations that are, I think, far beyond anything else that exists.
Okay, question. So since it is a distributed system, how do you partition your data? Is it like hash-based, value-based, round-robin, random?
So the question was, how do you partition the data since it's a distributed system? So one of the typical partitioning schemes that gets used, which is almost the default, is time-based partitioning. And actually, we don't in Pinot we don't allow updating of the data. So it's very useful for time series data. So you can just keep appending. So the time partition is actually a very sort of a logical way to keep partitioning your data sets. And again, it's the cluster manager that decides how to place the segments.
And
All right.
just
I
curious,
think,
how much is each partition?
Let's take the rest of the questions.
Okay, so
after
yeah,
this.
we have the red light flashing.
Yeah.
So we'll hang out on the side and we can chat further.
Thanks, everyone.
Thank you.
Thank you.